Hello everyone, today we're going to cover diffusion reaction problem. So we consider a straight cylindrical pore of length L and radius RP. We take a section of this pore, it will look like this. Essentially, here is the pore mouth at, let's say, at Z equals 0. And then the pore is impermeable, so nothing can, flow behind these walls. And so this is the axis of the pore. And this would be our radius RP, and the length of the pore is L. So this catalyst is present everywhere in the pore, and it's homogeneously dispersed. Then we're going to treat this reaction, even if it is in fact a heterogeneous reaction, we're going to treat it as a homogeneous case. So what this catalyst does is it transforms our species A into species B, and our reaction is zero order in A, or just zero order. And what this means is that our reaction rate, RA, can be written as just K, our rate constant, and K will have units of mole per meter cube per second. So here now given is the concentration outside of this pore. It's going to be Ca naught, and basically it's going to be the concentration at this interface. Okay. A has diffusivity dA in the pore. The system is a steady state. Also assume that A and B are present in very low concentration. At low concentration, we have inert gas is basically the majority of the gas, and we have a little bit of A and B in this inert gas. We need to use shell balance to find how the concentration of A varies as a function of Z. It's a cylinder. So the first question is this a two-dimensional problem? Is this a one-dimensional problem? So, well, the natural answer would be, okay, it's I would use cylindrical coordinates, so with Z and R, and it would be a two-dimensional problem. However, in this case, we're just gonna assume that the concentration in any cross-section is uniform. So uniform concentration in cross-section, or essentially we have a plug flow. And what that means is that we can treat this problem as a one-dimensional problem in the Z direction. Okay, so let's start with our shell balance. Okay, so the first step of shell balance is defining our control volume. And usually the way this is done, you have one dimension is really small. It's going to be an infinitesimally small dimension. So if this is our cylinder here, and this is our Z, our control volume will be defined as a disk. This disk here, thickness, let's say delta Z. And so our control volume will be this little disk of thickness delta Z, and the radius will be still RP. Okay, once we define our control volume, we do our species balance or mass balance. What that means is we have, in minus out plus generation or depletion equals accumulation. To find out what our in is, we need to start at essentially, we need to follow the direction that we decided is positive. So we would start here and we move until we hit the first boundary of our control volume in the z direction. And that will be our in. So our in will be mass transfer rate of A in the z direction at the position C. So in our notation, this means mass transfer rate, and the species balance is always done in terms of moles, per second. It's a rate. It's a rate balance. So yeah, mole per second. So minus out, we keep on going until we exit from our boundary, and we exit at z plus delta z. So this is going to be the rate out, so it's NAZ at z equals z plus delta z, plus our generation depletion term. Okay, so do we have a reaction in this control volume? So the question here is, do we have a reaction in this control volume? The answer is yes. Yes, we do. And let me change slide. Basically, the way we account for the reaction in volume, in infinitesimal volume, is, let's say, I'm going to draw again our control volume of thickness delta z and radius rp. This infinitesimal volume is delta v will be pi rp squared, so the area of the surface here, times delta z. So this is the volume of the cylinder. And we know that our rate, which is usually given, is, the rate of consumption of A is K. So, and this is given in terms of mole per meter cube per second, because this is a zero order reaction. So the way we get our rate of consumption is we need to multiply the rate A times our control volume for a homogeneous reaction. So what this means is that our rate of generation or depletion in our mass balance term will be Ra delta V, which is negative K delta V. I'm substituting Ra here, which is negative K Rp squared pi delta Z. Okay, so we can substitute this back in our balance. What we get, is our in term NAZ rate at Z equals Z minus NAZ at Z equals Z plus delta Z minus K Rp squared pi delta Z, and that equals to our accumulation term. Okay, so I'm going to write here, this is our in term minus out plus generation depletion. You guys can see that we have a minus sign here, which means this is depletion, right? Equals to accumulation. If Ca is our concentration, which is units of mole per meter cube, then the number of molecules of A in our control volume will be Ca times delta V, right? It's moles per meter cube times meter cube. So basically, the accumulation term tells us how many molecules are added or subtracted to our control volume over a given time. So essentially, it's a change in number of molecules of A over a given time. Okay, and then if you take a limit for very small times, then you can express this as a partial derivative. So we have d dt of Na, which can be written as essentially d dt of Ca delta V. Okay, but this is a fixed we have a fixed control volume, so we can rewrite this as delta V dCA dt. Okay, now I'm going to summarize all the term once more, and we'll have Na Z at Z equals Z minus Na Z at so our rates in and out Z plus delta Z minus K times our volume, which was pi RP squared delta Z equals accumulation. So again, pi RP squared delta Z, our volume term, times dCA dt. Now we can do our first simplification. We say that this is 0 because we're at steady state. So if we're steady state, we don't have any accumulation. That's a characteristic of steady state. So we can now express we go from a rate to a flux. And the way rates and fluxes are related is essentially a rate will have units of mole per meter squared, and a flux, so a rate is equal to a flux, which is moles per meter squared per second times the cross-section area times meter squared. You can see here that the meter squared just cancels. So we can rewrite our rate in terms of flux, and to do that we need the area. Okay, so we're looking at the rate which is crossing this cross-section, which has area pi RP squared. So what we can do is we say NAZ at Z rate equals the flux NAZ at Z. So again, the flux has no bar on top of it, times the area, which is pi RP squared. Okay, so let's do that and combine every single step. NAZ at Z equals Z pi RP squared minus NAZ at Z equals Z plus delta Z pi RP squared minus K pi RP squared delta Z equals to 0. Then notice that here this area is constant. Otherwise, I would have needed to include it in here. So next step, we divide by the volume delta V, which is pi RP squared delta Z. We're doing this because eventually we want to take a limit and have everything in terms of derivatives. So if we do that, you can see that we have NAZ at Z equals Z pi RP squared divided by pi RP squared delta Z. So this cancels out, but the delta Z remains, minus NAZ at Z equals Z plus delta Z pi RP squared divided by pi RP squared delta Z. So pi RP squared cancels out too, minus K pi RP squared delta Z equals 0 divided by pi RP squared delta Z. So here everything cancels out and only K remains. So we can write this as negative, and now in a second we're going to see why that makes sense. Negative NAZ at Z equals Z plus delta Z minus NAZ at Z equals Z minus K equals to 0. Okay, so now the next step would be we want to take the limit for delta Z going to 0 of this expression. And the reason why we want to do that is that we're going to go from a kind of differential form to a derivative. So I just want to remind everybody the definition of the derivative. We have a function y is a function of x, and we're it could be any function, and we're trying to take the derivative at this position x, and this is basically y. So we're going to have x plus delta x here, and y plus delta y. So the derivative essentially is slope here as delta x becomes smaller and smaller, and it becomes a tangent. So df dx is defined as the limit for delta x going to 0 of f of x plus delta x. So this point here minus f of x divided by delta x. Okay, this function here, delta z, we have limit for delta z going to 0 of naz at z plus delta z minus naz at z. Then this is equivalent to our definition of derivative. So this will be equal to d naz at z over dz. So summarizing, we can rewrite, and we should not forget our negative sign there, the derivative of a flux in the z direction with respect to z minus k equals to 0. Okay, so this is our first point. Okay, so now this is not enough because we don't have a concentration here, so we need to relate the flux of A with concentration. And how do we do that? We use Fick's law. So the most general way to write Fick's law is following. We write the flux of A, for example, in the z direction is equal to negative dA, the diffusivity times the gradient. Let's only consider the z direction here, so dCA dZ. And then this is not enough. We also have our CA divided by C total times NA Z plus NBZ. So essentially, this term here on the right is our kind of convective term, or another way to call it would be our concentrated mass transfer term, while our term here is our diffusive term. And in this case, we can ignore this term on the right because essentially this is small. So it's basically 0 because it's dilute. So that's one of the assumptions that we made in the beginning. And this means that basically CA is much smaller than C total. And so it's, the relatively to C total, concentration total, it's we can ignore it. So now we substitute this in our mass balance, and what we get is, we have D, dZ, and we had a negative there, dA, dCA, dZ minus K equals 0. And then we can bring dA outside of the derivative because it is constant. So when we do that and we account for sign, we have dA, second derivative of CA with respect to Z minus K equals 0. So we can rewrite this as second derivative of CA with respect to Z squared equals K divided by dA. Let's quickly check our units see if we did anything wrong. This is always a good habit. So this is moles per meter cubed divided by meter squared needs to equal, this is moles per meter cubed per second divided by meter squared per second. Okay, this is our diffusivity units, so it's length squared per second. So let's see if these units cancel out. Second and second cancel out, and here we're left with moles per meter needs to equal, and here too we have moles per meter. So this is good.